Now let's take a look at the electric fields when they hit a conducting surface, and then that'll use that as a segue into Gauss's law. When electric fields hit a conducting surface, what's going to happen is the charges are going to rearrange themselves such that the net electric field is going to be zero inside of a conductor. So we expect the electric field to be equal to zero inside of a conductor. Let's just take a look here. Suppose I place a positive charge right here inside of some conducting sphere, then these charges inside of this metal conducting sphere, well, they're free to move around. So the negatives are all going to be attracted to that positive guy in the center, and the positives are all going to be repelled from that positive guy in the center. Now let's just take a quick look here. I know positive charge, I'll draw the electric field away from it. And I know negative charges, I draw the electric field kind of coming towards it. The net result is the sum of those electric fields are going to perfectly cancel out this electric field right here, and so we're going to get the electric field is equal to zero inside of the conductor. Outside of the conductor, you can kind of see that all we have is the electric field from the positive guy here, and what's going to happen is the electric field is just going to kind of pick up where it left off, and we'll use Gauss's law to calculate the magnitude of this electric field. Now what's going to happen just at the very surface is the electric field is going to have only a parallel component. There will be no perpendicular components. We will not have electric fields kind of looking like that at the surface. If the electric field did exist in this direction, then this charge would kind of slide over there. So the charges would move. So the electric field must be perpendicular. It will not be parallel at a surface. This is going to take me to something called Gauss's law, which is going to let me calculate the electric field for funny shaped objects like spheres and cylinders and stuff like that. To use Gauss's law, we need to introduce this concept of flux, which you can kind of think of as flow through. And essentially we'd be looking at the flow of electric field lines through some area. Kind of the symbol for it is going to be this funny shaped guy right there. And it's going to be related to the electric field multiplied by the area that this electric field is kind of punching through. Technically speaking, it's actually what we call a dot product, but more often than not, we're just going to say it's going to be the magnitude of the electric field multiplied by the magnitude of the area multiplied by the cosine of the angle in between them. To figure out the direction for the area vector, what we do is we draw a line kind of perpendicular to the surface that we're talking about, and that's going to be the direction of this area vector, and the angle between that area vector and the electric field is going to be the angle that we use kind of right here. The unit for electric flux, here we have a unit of Newton per Coulomb. Here we have a unit of area, so it's just going to be Newton meter squared per Coulomb. Now, if we consider any closed surface, suppose I have some box that I drew up here, and I have some electric field kind of punching in to that box. I could calculate the flux. It's going to be the electric field multiplied by the area, cosine of the angle in between them. You can kind of imagine that same electric field punching out of this box over here, and in this case the area vector is going to be drawn by my blue arrow, and here it's going to be in that direction. So you can kind of see that here we're going to have cosine of 180 for my flux. Here when I go ahead and calculate my flux, I'm going to have a cosine of 0, and that's going to be multiplied by the area in the electric field. So area electric field is going to give me my flux. Now you can kind of convince yourself that cosine of 180 is -1, so all the flux going into the left side of the box is going to be leaving that side of the box, and the net flux is going to be equal to 0. The only way I'm going to get some flux is if I have some charge enclosed. So if I put some charge in there, then I'm going to have some electric field lines kind of punching out. So what Gauss's law says, very important, is that for any closed surface, I can write the electric field multiplied by the area is simply going to be equal to the charge enclosed divided by this permeability of free space. So my flux is simply going to be equal to the charge enclosed divided by the epsilon naught. We can it's kind of an abstract concept, but it turns out that if we have situations with a high degree of symmetry, we can use this to find the electric field. I just have to make sure that I draw my area perpendicular to the electric field, and then I can kind of reduce this to be equal to the electric field multiplied by the surface area is equal to the charge enclosed divided by epsilon naught. So let's go ahead and use this. If I draw my area, let's say draw a perfect sphere here, and I enclose this charge, here my area is always going to be perpendicular to my electric field if I was a very good artist. And so I can say that the electric field multiplied by the area is simply going to be equal to the charge enclosed, here it's just Q, divided by the permeability of free space. My area is just going to be the area of the sphere, which is 4 pi r squared. So the electric field multiplied by 4 pi r squared is equal to the charge enclosed divided by the permeability of free space. You can kind of rearrange this to say that the electric field is going to be equal to Q divided by 4 pi epsilon naught radius squared, where the radius is simply the radius of my sphere. Now if I were to draw my Gaussian surface out here, still a sphere, then what's going to happen is the magnitude of this charge is going to be equal to, or the magnitude of all of these charges is going to be equal to the magnitude of that charge, and so my Q enclosed is going to be equal to 0. So for this one, I'd say my electric field multiplied by area is going to be equal to 0 divided by epsilon naught. Since area cannot be 0, and that's just a constant, that says that my electric field must be equal to 0. And similarly, if I draw it out here, again, perfect sphere, electric field is going to be equal to charge enclosed divided by epsilon naught. All of these positive charges are going to be the same magnitude as all the negative charges, and so I'm going to say that the electric field is going to be equal to charge enclosed divided by 4 pi epsilon naught radius squared, where that's the radius of my sphere. We can also apply Gauss's law to figure out the electric field inside of a capacitor or two charged plates. Essentially what we do is we say this charge is going to be uniformly distributed throughout the area, so there's going to be some surface charge density. It's just going to be the charge divided by the area. Now we say, okay, I'm going to go ahead and draw some surface, and what's going to happen is we can say that the electric field multiplied by the area is going to be equal to the charge enclosed divided by epsilon naught. So here the electric field is equal to 0. Right here the electric field is going to be perpendicular to the area, so there's going to be no flux there. Similarly here there's going to be no flux. The only thing we're going to have is this electric field multiplied by the area. Now my charge enclosed, that's simply going to be equal to the surface charge density multiplied by area. So my charge enclosed is going to be the surface charge density multiplied by area. And I can see that my electric field is going to be equal to this surface charge density divided by epsilon naught, forgot that guy. And you can see that this is just going to be some constant that depends on the area of the plates and the charge on them. See, the electric field is not going to vary with distance. It's going to be constant, just like I said when I talked about this slide earlier.